Naveen Kumar, having 15 years of teaching experience in both GATE and ESC. We discuss about the topic optical communication, which is a part of your EMT subject for GATE 2021. The complete subject of optical communication that we study in the GATE is of 4 parts. The first one is a basic introduction. The second one is we see about the review of optics. Third one is types of fibers, and the fourth one is about the attenuation or losses. So before starting about this subject, we will see about the first part, that is called as introduction. So in this introduction, we see about the elements of optical communication systems. So first thing is, if we see about the frequencies that we use in optical communication system is 10 to the power of 12 Hz to 10 to the power of 16 Hz. So if you see about this frequencies, the frequency is going to be starts from terahertz, which is said to be called as 10 to the power of 12, is called as the terahertz we are having. So the terahertz of frequency is the starting frequency of optical or light region. If you see the complete electromagnetic spectrum that we studied about, that kilohertz, megahertz, gigahertz. After gigahertz we see about the terahertz. Okay, and once we talk about that terahertz, the terahertz is the region where the light will going to be starts. So if you see about the light region, or we can also tell about the optical region, that is to be present from 10 to the power of 12, 10 to the power of 13, 10 to the power of 14, 10 to the power of 15 and 10 to the power of 16. Where 10 to the power of 12 is called as the terahertz and 10 to the power of 15 is said to be called as the pentahertz we are having, said to be called as the pentahertz. If we see that that is the light region which is having these frequencies are going to be present for the light region, and in that light region it is totally divided into the 3 parts. The first one is said to be called as the infrared region. It is called as IR region also. It is called as the infrared region. The total light region is divided into the 3 regions. The first one is infrared region. The second one is said to be called as the visible light region. It is called visible light region. And the third one is called as UV region, ultraviolet light region we have. So if we see about these 3 regions, infrared region, visible region and ultraviolet region. So as long as the frequency is going on increases, just try to understand, that's very simple. So we studied that we have a copper cable which can withstand up to kilohertz. After that we study about the coaxial cable. We see in the EMTL also about the coaxial cable where we calculate our impedance, characteristic impedance, Z0 is calculated, having inner conductor and outer conductor is present. So that is having in terms of megahertz of frequency can be withstand by the coaxial cable. If you going on increasing the frequency, then what happened is the coaxial cable cannot withstand that frequency. Then we come across the another one that is said to be called as the waveguides. If you see about the waveguides are going to be withstand up to a frequency of gigahertz. So after the gigahertz, the waveguides are also not supposed to be present, because the reason is, if you see the waveguides, the dimensions of the waveguides is inversely proportional to the frequency. As long as the frequency is going on increases, if you increase the frequency, the dimensions become very small. Then the A and B, if you consider rectangular waveguide, the length and breadth A and B will become quite small. They become quite small in the sense means the designing purpose and all those things are a challenging task for an engineer. Therefore, we cannot going to be consider the waveguides greater than the gigahertz frequencies or less than the gigahertz frequencies. That's why mostly when we study about the waveguides, we are just focusing only in the that gigahertz frequency range only. And another important thing, that after the gigahertz, the waveguides are not supported, and obviously all these are electrical signals, but after the gigahertz, the terahertz will come. The terahertz is the light signal. Then we required a cable said to be called as the optical fiber. So that is the transmission medium which we are using is an optical fiber we are using, which is also called as optical waveguide also we can call it as, but we mostly use optical fiber as the terminology in the entire classroom. Okay, so now we will see about the next one, that is said to be called as the wavelength. If you see about the wavelengths are going to be present from 10 to the power of 6 nanometers to 10 nanometers of wavelength we are using. But most of the wavelengths that we are going to be using in our optical communication is from 800 to 1600 nanometers, and we are operating in a region called as infrared region. That is, I told you already that we have three regions. So the region that we are operating is nothing but an IR region. IR region stands for the infrared region. Next one is about the transmission line. The transmission line we are using is called as a optical fiber. It's called as the optical fiber we have. So after that, as long as the frequency was going on increases, that means our carrier frequency is going to be very, very high, then the bandwidth utilization ratio is high, and also it offers a very high bandwidth. That's why after gigahertz, we are moving to terahertz. The reason why we are operating in terahertz is we get BUR, that is called as your bandwidth utilization ratio. BUR is going to be 10% of carrier frequency FC. If your FC is in terms of terahertz, then your bandwidth utilization ratio is going to be equal to that of into 1 terahertz. If you take particularly as 10 terahertz we can take, then automatically we are going to be having 1 terahertz of bandwidth is present. So 1 terahertz of bandwidth means it's very huge amount of bandwidth which is going to be offered by the optical fiber cable. So that's the reason we are going to be shifting from gigahertz to terahertz, and we are operating in optical fiber cables. So that's why this is the one form of transmission line. So that's why we are studying about this type of transmission line, how light is propagated, and what is the phenomena that occurs in the optical fiber cables. We can see in the coming parts of the optical communication system. So first point that we considered here is, if you see that the frequency is very, very high, we got the bandwidth is very high. And second point is, if frequencies are going to be very high, we can always consider that in terms of wavelengths. That means when electromagnetic waves at ultra high frequencies we can consider it, then we can consider the wavelengths instead of frequencies. So that's what the wavelengths I want to tell to you for your infrared region, visible region, and UV region. So if you see about the infrared region, the operating wavelength is going to be 770 nanometers to 10 to the power of 6 nanometers we are having. That is 770 nanometers to 10 to the power of 6 nanometers is for the infrared region we have. If you see the visible light is the light where the human eyes will respond. If you see the human eyes will respond to that visible light, like rainbow colors, which were violet, indigo, blue, next green, yellow, orange, and red. So that is what we see about the visible light we have. The visible light is going to be having the wavelength from 390 to 770 nanometers of wavelength is present. In that wavelength, it is going to be operating. So in some books, we can tell the visible light region is having a wavelength of 400 nanometers to 800 nanometers. Okay. So next one is UV region. If you talk about the ultraviolet region, it is going to be having the so-called said to be called as 10 nanometers to 390 nanometers is the wavelength for ultraviolet region. So out of all these regions, we are going to be studying about the infrared region in our optical communication system. So now we can see about the elements of optical communication system. So that's the reason why we are going for the optical fiber cable is it is offering a huge amount of bandwidth and it is also offering a less amount of losses. So that's why we are operating it in the at very high frequencies we have. Okay. Please copy this part. So elements of optical communication systems. So you see about the elements of optical communication system, the first block that we are having is said to be called as the drive circuit. Said to be called as the drive circuit we are having. The second one is nothing but an light source. So we have the light source. And for this drive circuit, the input that we are going to be given is nothing but an electrical input that we are giving you the electrical input is given. So the drive circuit output was given to the light source. The light source was going to be connected through a fiber with the help of a connector we are having, said to be called as the connector. So after that it is going to be having a splice. Splice will make the two fibers to connect to each other, which was going to be shown in the figure. So after that the splice was going to be given to a coupler. A coupler is a device which can couple the optical energy to the other circuits or to the more number of circuits we are having. It's called as the optical fiber, and this one is said to be called as the other circuits we are having. The output of that coupler optical power what we are having will give to the other circuits. After that that was passes through a repeater. So a repeater is a device which we are going to be repeats the signal and remove the noise. That is, repeats the signal, regenerates the signal once again, but removes the complete noise. Okay, therefore we are going to be using the repeaters for long distance transmission. So if you see about the repeaters, the repeater block diagram was going to be as shown in the figure. So we have here an optical receiver, and here we are having optical transmitter. So once in the block diagram I explained to you. So after that we can see about the output was given to the block said to be called as the optical detector, which is said to be called as light detector or optical detector also. Output of the optical detector was going to be passed through an amplifier. Then it is going to be given to a signal restorer. So we have a signal restorer. The signal restorer will restore back to the original form of a signal. That means it is going to be obtained the output as an electrical output. So to be called as the electrical output we have. So this is completely about the block diagram we are having. So here also we are using a connector. Okay. So see here. So what we are going to be using here is said to be called as a connector. Connector always provides temporary connection. So it will always provides temporary connection between the light source and fiber to fiber. Also, it is going to be providing the connection between fiber and detector. That is fiber and detector we are having. So your connector is going to be a device that to be called as a mechanical interface. It is a mechanical interface we have. So connector always provides a temporary connection we are having. So next one is splice. Splice will always providing you the permanent connection. So permanent connection between fiber and fiber was going to be provided by the your splice we have. So that to be called as the permanent connection we are having. That to be called as the splice we have. So after that, whatever the signal we are getting will comes to the coupler. Coupler will going to be distribute the power to the other circuits. It is going to be distributing the optical power to other circuits. So to other circuits, it is going to be distributing the optical power. If you see about the coupler, this coupler is of two types. One is said to be called as the your star coupler, and second one is called as T coupler we are having. So if you see that the input, electrical input we are giving, that electrical input, whatever the voltage we are having, that voltage was going to be converted into a current by using a drive circuit, which was going to be acts as a voltage to current converter. It is going to be acts as a drive circuit, acts as a voltage to current converter. So after that, that current was going to be passed through a light source. The light source will going to be convert this current into the optical signal, so that we are having the optical signal is present. So what the light source basically doing is, the light source basically doing E by O conversion. So it is converting electrical into optical. Your electrical signal was going to be converted into optical signal. Why? Because means here we are going to be using a fiber. For your fiber, it can going to be carrying the optical signal. So carrier, for the carrier is going to be here as a optical, and the fiber will also carries that optical signal. So we need to convert your electrical signal into the optical. That conversion will take place with the help of a light source. Such a light source we are having is nothing but of two types we are having. One is called as LED, light emitting diode, and a second one is said to be called as the laser, light amplification by stimulated emission of radiation. So we study about these two light sources very clearly in our EDC part about the semiconductor devices of optical semiconductor devices. So one is LED light source, other one is called as a laser we are having. So that light source is LED or laser will converts into optical signal, will pass into a fiber. From your light source, it will couple into a fiber with the help of a connector, and the splice will make a connection of the two fibers has to be make a connection is done with the help of a splice or splicing. So next one is we have the coupler. It's a device which can going to be couple the power to other circuits. That is, the amount of power we are getting is distributing to the other parts of the circuit we have. So next one is we are coming to the repeater. Your repeater is an electronic device. Whatever the repeater we are having is an electronic device we are having. It's an electronic device. Therefore, what happened is, whatever the input we are getting is optical, and output also we need to have that converts into the pass into fiber in the form of optical only. But the device want in terms of electrical signals. So we use a receiver, which is the reverse operation of your transmitter. Nothing but an optical to electrical conversion was done. So here we will got electrical. So in the repeater we are going to be performing that electrical operation was done, and we can give that to the transmitter. Transmitter will convert that electrical once again to optical and pass into a optical fiber. So optical detector will do the reverse operation, which will going to be said to be called as electrical conversion. was going to be present. So we are converting optical to electrical conversion we have. So your optical signal was going to be converted into the electrical, and you are having an amplifier which can amplifies the signal. The optical detectors that we are having is of two types. One is called as PIN photodiode. Second one is called as the APD, avalanche photodiode was used. So in the amplifier was going to be used to amplify the signal. Signal restorer will restore back to its original form. Electrical input will comes back as an electrical output. So this is what we said to be called as the elements of your optical communication system we have. So if we see about this complete thing, the laser was going to be used in optical communication, and we are also studying about the diode called as PIN photodiode is used. The beautiful advantages of optical communication system is, the first advantage is bandwidth is very high. The second one is the losses are very less. Third one is security is very high. It's not possible to cut this fiber and going to be make a alternate connection. Why? Because means a specialized training person is required. It's not like copper wire. You cut the copper wire and once again you put a copper wire and put a tape. The connection has to be formed. This is a security point of view. It gives a very huge amount of security will be present. So next one, there is no corrosion. Okay, and the weight of the fiber was going to be very less. If you use a specific materials like plastic, we can use. Okay, and the size is very small. Right, the size of the fiber was going to be very small. There is no corrosion. Abundant raw material is available. Huge amount of raw material is available. Because of all these reasons, you are going to be shifting from copper cables to optical fiber cables. Okay, next, disadvantages. So there are three disadvantages. The first disadvantage is it have a very huge bandwidth, but we are not utilizing the bandwidth effectively. So we are not utilizing the bandwidth effectively is said to be called as the first drawback regarding to the bandwidth. And the second one is, we will tell about the optical fiber cable is, so specialized training and equipment is required. So specialized training and equipment people are going to be required for this optical fiber communication system. So for example, a normal engineer also cannot going to perform the splicing. He needs some training, some equipment is going to be required to perform that particular splicing. It's not the case with your copper wire. Copper wire can be done very easily. You can go into twist it and you get the copper wire can be uptime. Okay, copper wire connection can be formed, but optical fiber connection cannot be going to be uptime. And most important thing is, it cannot be work in the nuclear environment where lightning of darkening of light of fiber is done, where the light cannot go into propagate through it. So that's why these are what we said to be called as the disadvantages and advantages. Okay, so this is the small introduction part that I want to give before starting about your elements of optical communication system. So the next topic we can see of the introduction topic, right? The next one is said to be called as the review of optics. Okay, please copy this part. Next topic is review of optics. So before going to start about this one, I want to tell you about the nature of light. If you see about the nature of light, so the light is having a dual nature. If you see about the nature of light, it is having a dual nature. The first one is said to be called as the wave nature. So wave nature was going to be proposed by the Maxwell, and C is equal to 1 by root of epsilon naught into mu naught, which will going to be gives about the velocity of the light. So wave nature, we have seen the reflection, refraction. So all those things are going to be studied when we talk about the wave nature. And second one is said to be called as the particle nature. Said to be called as the particle nature. Particle nature was proposed by the Planck and Einstein. So Planck and Einstein both has proposed this particle nature. So according to the particle nature, energy present in the photon is going to be directly proportional to the frequency. That is, EP is equal to h into f, where h is said to be called as the Planck's constant. You can like this also, EP is equal to h into c by lambda also. Okay, so h is called as the Planck's constant. We have that h is said to be called as 6.626 into 10 to the power of minus 34 joules second. We are having, which is said to be called as the unit for Planck's constant we are having. So this is about the particle nature and wave nature. So whenever the light was traveling from one point to the another point, it has to be satisfies the wave nature, and whenever the light was going to be generating, it has to be satisfying the particle nature, where we study about that called as the photon. That's why we are writing as a energy in the photon we are having. EP is called as the energy present in the photon we are having. So this photon, which is going to be studied by us in our devices like light source and the photo detector, when we see, we have the particle nature is present. But whenever we are going to be studying about the light was traveling from one point to the another point in optical fiber cable in a guided medium, then we can going to be seeing about the nature called as the wave nature is present. That's the first thing, which is called as nature of light we are having. And second important thing is that is said to be called as the optical power we are having. It's called as optical power. Optical power is also said to be called as the radiant flux. It is called as radiant flux. So we know that power is nothing but an rate of change of energy we are having, which is called as dq by dt, or energy by time. Total energy by total time is also said to be called as the power we are having. So if you talk about this power P is equal to dq by dt, so the power was going to be measured, P is measured in dBm or dB mu we are having, which is measured in terms of dBm or dB mu is the value we have. So power in terms of dB is given as 10 into log of P of base 10, which is given in terms of dB. Here the reference is in terms of 1 watt. What are the dB we are writing? It is in terms of 1 watt we are having. But when you take about the same thing, that is in terms of dBm, power in terms of dBm is given as 10 log of P by 1 into 10 to the power of minus 3 of base 10, which is called as dBm, is the value we are having. So next one is, so power in terms of dB mu, you can have, is given as 10 log of base 10 of P 1 into 10 to the power of minus 6 dB mu is the value we are having. So to be called as the dB mu is the value we have. So this is completely what we said to be called as the optical power or radiant flux we are having. So generally we know that dB plus or minus dB is going to be equal to dB, and once we write about that dBm plus dB was going to be equal to that of dBm. So similarly dBm minus dBm is also going to be equal to dB we have. This is to be called as the dB is going to be obtained to us. So this is completely about your optical power, which is also called as radiant flux we are having. So this is about the review of optics. We will see about the next one. Okay. Next one is refractive index. Which is denoted by small n. Refractive index is defined as the ratio of velocity of light propagating in vacuum to that of velocity of light propagating in medium. So if we see about the definition, that is velocity of light in vacuum to that of velocity of light in medium. So velocity of light in vacuum was going to be given as c, and velocity of light in medium was going to be given as v, small v. So if we see about that, this is said to be called as the definition of your refractive index. If you see that the n value should always be going to be greater than 1. The reason is, for vacuum, your v is equal to c, then your n is equal to 1. If you consider velocity of light in medium, that medium is going to set to be as a vacuum medium. Considering as a vacuum, then v is equal to c cancel, n is equal to 1. Then every time refractive index must going to be n is greater than 1. So whenever the light was moving from one medium to the another medium, there must be having some change in the wavelength, but not have any change in the frequency. So that we can going to be given as like this. C is equal to that of. So your C is going to be written as the value called as C by lambda, that is going to be given as the value called as the frequency, which is given as f into lambda naught we are writing. Generally f is equal to c by lambda, and we are writing about c is equal to lambda naught because of that c. And v in some medium, that is equal to f into lambda was going to be given. See that f frequency does not changes. So which will change? Change is present only in terms of its wavelength. So therefore, we can write our refractive index n is equal to c by v, f and f get cancelled out, which is given as lambda naught by lambda also. So for some of the materials, we can consider the refractive index. So refractive index for vacuum is going to be equal to that of n is equal to 1. Refractive index for air, value of n is equal to 1.0003, which is approximately equal to 1, we can take it. So next one is refractive index for water, value of n is equal to 1.33, and refractive index for ethyl alcohol. Okay, so ethyl alcohol, so n value is equal to 1.36 we are having, said to be called as the ethyl alcohol we are having. Next one is for fused quartz. So writing about for fused quartz, n is equal to 1.46. So similarly for glass, so writing about the glass, n is equal to that of 1.5 we have, which is said to be called as the glass. So next one is we will tell about the another important one, that is diamond. The refractive index of diamond n is equal to 2.42. So for silicon, n is equal to 3.2. So this is the refractive indexes for some of the standard materials or standard mediums we are considering. So mostly we will have a requirement of glass will going to be considered, because fibers are manufactured with the help of plastic as well as the glass. So that's why we are going to be considering the glass. Okay, so please copy this. Right. The next topic that we have is Snell's law. The fourth topic is said to be called as the Snell's law we are having. So Snell's law defines the angle of refraction. So angle of refraction was going to be represented by theta 2. So theta 2 can be going to be defined with the help of the Snell's law we have. Okay. So consider two mediums. This is said to be called as the medium 1, said to be called as N1, said to be called as medium 2, it's called as N2 we are having. So once we talk about this medium 1 and medium 2, two different mediums having two different refractive indices, that N1 and N2 are going to be present. So next one is a line drawn exactly perpendicular to the boundary between the two mediums, where the light ray will incident on the boundary is said to be called as normal. Okay, now see. So light ray was going to be incident. Just try to understand this. So light ray was going to be incident here. So once the light ray was going to be incident, line drawn exactly perpendicular to the point of the incident light is said to be called as normal. Said to be called as the normal we are having. So this is going to be said to be called as the incident ray, and this is called as theta 1. This is called as the angle of incidence, said to be called as theta 1. So line drawn exactly perpendicular to the point of incidence of light is called as the normal we are having. So if N1 and N2 both are same, the light ray will going to be travel, which is shown in a dotted line. That is, your N1 is going to be equal to N2, and this is theta 2 angle of refraction. Theta 2 value is equal to theta 1 whenever both the two mediums are going to be same. But when the two mediums are not same, N1 and N2 are not same, and N1 is greater than N2, then the light ray will move away from the normal. It moves away from the normal when N1 is greater than N2. Whenever your N1, medium 1 is greater than medium 2, that means moving from denser to rarer medium. So moving from denser to rarer medium, then definitely theta 2 is greater than theta 1. Theta 2 is greater than theta 1. This is going to be said to be called as the refracted ray. It's called as the refracted ray we are having. So I will tell you that one small point here. Light is moving from denser to rarer medium, angle of refraction is greater than the angle of incidence and light moves away from normal. So light moves away from the normal. See, the light is moving away from the normal. It is moving away from the normal, have some bend and moves like this. The light is moving in this way. It's called as a refracted ray we have. For example, N1 is rarer and N2 is denser. Just follow the red color pen. So the light was going to be moving towards to the normal. So this is the case. It will move towards to the normal. This angle is called as theta 2. So N1 is less than N2, then definitely theta 2 is less than theta 1 we have. The theta 2 value is going to be less than theta 1 we are having. This is said to be called as that the light is going to be moving from rarer to denser medium. Moving from rarer to denser medium. And the angle of refraction is less when compared to the angle of incidence. Okay. So here light moves towards the normal. The light was going to moving towards the normal we are having, which is as shown in the figure. Now Snell's law was going to be used to tell about this angle of refraction. Snell's law always gives the relation between refractive index and the angle of incidence, or refractive index and the angle of refraction. So at this point I am going to applying the Snell's law. So Snell's law, N1, refractive index is N1 into sin theta 1 for sin theta 1, and that is going to be equal to that of N2 into sin theta 2 we have. So N1 into sin theta 1, that is equal to N2 into sin theta 2 is the value we have. So we can write in this way. It's called as sin theta 1 upon sin theta 2 is going to be given as N2 by N1 we are having. It's called as N2 by N1 is the value we have. This is said to be called as the Snell's law, which will tell us about the theta 2. If you know N1 and N2 and we know about the theta 1 angle of incidence, then we need to find theta 2 very easily by using this one. Okay, by using the Snell's law formula. Please copy it. Please copy that part, all of you. Right. The next one is critical angle. Critical angle is represented as theta c. Defined as theta c. So critical angle is defined as the minimum angle of incidence at which the light ray may strike the interface of the medium and result in the angle of refraction of 90 degrees or greater. So said to be called as the critical angle we have, said to be called as theta c we are having. So whenever theta 2 is 90 degrees, just see here. So whenever theta 2 is going to be equal to 90 degrees, your theta 1 is going to become equal to theta c. That means theta c is going to be nothing but an theta 1 whenever theta 2 is going to be equal to 90 degrees. So just see here. said to be called as the medium 1 having a refractive index n1 and medium 2 having a refractive index n2. So light was going to be incident. Line was going to be drawn perpendicular to it, said to be called as the normal. And the angle of incidence that we are going to be having is said to be called as the theta 1. So here, if your angle of refraction, your theta 2 is equal to 90 degrees, then this theta 1 is going to be equal to that of theta c we are having. So 90 degrees or greater also, said to be called as the theta c is present. So now just see here one small point. So writing about our Snell's law. So consider the Snell's law. We study like this, sin theta 1 upon sin theta 2 is equal to that of n2 by n1 we are having. It's called as the Snell's law. So now we can put your theta 2 is equal to 90 degrees. Then theta 1 become theta c. So theta 1 become theta c. That is equal to that of n2 upon n1. Sin 90 is 1. So therefore sin theta c is equal to n2 by n1. So theta c is equal to that of sin inverse of n2 by n1 is the value we are having. So this is what said to be called as the theta c value we are having, which is called as the critical angle. Critical angle is the minimum angle, okay, of the incident ray at the interface or the boundary where the light was going to be incident, whose angle of refraction is equal to 90 degrees or greater. That's the definition. We said to be called as the critical angle theta c is present. Please copy this one, all of you. So next one is total before the acceptance angle. We can see about the total internal reflection. Total internal reflection said to be called as TIR. It's called as the TIR we are having, right? If angle of refraction theta 2 is 90 degrees or greater, and the light which was going to be incidented will reflected back into the same medium is called as total internal reflection we have. Okay, just see here. So considering a boundary between the two mediums, medium 1 whose refractive index is n1 and here medium 2 whose refractive index is equal to n2 we are having. Light ray was going to be incident. Line drawn exactly perpendicular to that is said to be called as your normal, said to be called as normal, and this one is said to be called as the angle of incidence, which is called theta 1. Now see here angle of refraction theta 2 is going to be equal to 90 degrees. The theta 1 will now become equal to theta c. That's called critical angle. Okay. So this ray is said to be called as the incident ray we have. Now just see the concept. Whenever the light ray was going to be incident with an angle theta 1 greater than theta c, this is said to be called as the incident ray. Tell about that, it is called as theta 1. Your theta 1 is going to be greater than theta c. Then the light ray will get reflected into the same medium, which is said to be called as the reflected ray. It's called as a reflected ray, and that angle is going to be said to be called as theta 3. Whenever your theta 1 is greater than theta c, we are going to be having the total internal reflection will takes place. So if total internal reflection will takes place when theta 1 is greater than theta c, then only your theta 3 is going to be equal to theta 1, which is the condition for TIR, total internal reflection. So if this condition is going to be present, the light ray does not going to be pass into another boundary. It is going to be present in the same medium, which is called as TIR. This is very important principle that is used in optical fibers. The principle used in optical fibers we are having. So what's the principle that we are using is TIR. Okay, the principle used in optical fiber communication is TIR, total internal reflection we have. So now see that another one. Whenever the light ray was going to be incident with an angle less than theta c, the light ray was going to be incident with an angle less than theta c, then depending upon the N1 and N2, the light ray was going to be refracted. That is, it moves into the another medium. So assuming N1 is going to be greater than N2, then theta 2 is going to be greater than theta 1. And we can tell very clearly such that the light ray was going to be not reflected, it is refracted. That refracted was considered to be as a lost in the propagation in optical communication system. We always required the reflection. That is called total internal reflection is required. So this one, when this happens, when theta 1 is less than theta c, see that red color one, theta 1 is less than theta c, so this is going to be happen where the light was going to be having refracted, which is going to be considered to be as a loss. So to be called as a lost or loss of your light ray. So this is the principle that we are using in your optical fiber cables. Okay, please make note of this one, all of you. Next one is said to be called as the acceptance angle. So your acceptance angle is said to be called as theta in or theta a also we can write. So acceptance angle, theta in or theta a notation, both are going to be same. Now see here, we are considering the core of the fiber. It's called as the fiber, whose refractive index of the fiber is going to be said to be called as N1, which is called as the core. This core was manufactured by using the glass. So the outer one what we are going to be seeing is nothing but an air whose refractive index N0 is going to be equal to 1. Now this acts as a boundary or this acts as a boundary. So whenever the light was going to be incidented from the light source, in the two boundaries, light has to be confined within the core to take total internal reflection. So within the core, it has to take the total internal reflection has to be present. Now just see here, This is the fiber. The major problem with this fiber is whenever we put another fiber close to this one, then of same material N1, then we cannot have a discrimination between these two fibers. Light will pass into that fiber. And the strength, mechanical strength of the fiber was going to be very less because pure form of glass was going to be used. And contamination is also very, very high. So to avoid these problems, what we are doing is, we are going to be putting some clad. See, the refractive index of such clad is going to be equal to that of N2. And by putting this clad, we can going to be differentiate between the two fibers very easily. That is for fiber 1 and fiber 2, we can going to be bunch all the fibers. The light within fiber will confine to the particular fiber only. So adding this clad will going to be provide three things. First thing is, it can provide the good isolation between the two fibers. Second one is, it avoids the contamination of the core. Third one is, it is going to be providing the mechanical strength to the fiber. So like this, the fiber was going to be having both core as well as clady was going to be present. Okay. So this is about our fiber structure, how that fiber will having core and clady. So what the requirement of that core and clady is present. Now I am inserting the light here. It is said to be called as the incident ray. Line drawn exactly perpendicular to that is said to be called as your so-called said to be called as the normal. We have, so it is called as the normal. So this is going to be given as the incident ray. It's called as theta in, said to be called as normal. We have. So this is that the light was going to be incident. Okay, said to be called as theta in. So light was, this is air, this is completely called as air, refractive index N0 is 1. Light is going to be moving from rarer to denser because it is glass. The refractive index of glass is 1.5, which is greater than the refractive index of air. So light is moving from rarer medium to denser medium. So it will going to move close to the normal. So it is going to moving close to the normal. It's close to the normal. And this angle is going to be said to be called as theta p, critical propagation angle. Theta p. With this critical propagation angle only, the light will going to pass into a fiber from the outside into a fiber. And here total internal reflection will done is called as theta c is present here. And the light was going to pass into a fiber with total internal reflection. It is completely what we see about how the light is going to pass into a fiber. So don't get confused. Light is incidenting from rarer to denser medium. Light is moving into a fiber so that it is moving towards to the normal. This angle is called as the critical propagation angle. With that propagation angle only, the light is going to pass into a fiber. So amount of light that can going to be allowed to pass into a fiber is said to be called as the acceptance angle. It's called acceptance angle we are having. If you see the definition of acceptance angle is the maximum angle in which external light ray may strike the interface and enter into the fiber and also propagate through the fiber is called as the acceptance angle. So this is called as the acceptance angle we are having. So this point is called as A. Apply Snell's law at A. Snell's law gives the relation between refractive index and the angle. Okay. So refractive index here is N0 angle, that is equal to sine of theta in, and here refractive index is N1 into sine of theta p we are having. So your n naught value is equal to 1. So sine theta in is equal to n1 into sine theta p is one formula for your acceptance angle, which depends upon the critical propagation angle we have. Now just see here, it is going to be forming one triangle here. So forming one triangle. Just I am going to be considering that triangle. So this is going to be given as theta p. This is called as theta c we are having. So we studied in the classroom as sine theta c is going to be equal to that of n2 by n1 we are having. So sine theta c is equal to n2 by n1. So by this condition we know that n2 is said to be called as the your opposite side by hypotenuse. So for theta c here n2 is going to be that opposite here and hypotenuse is equal to n1. Then definitely the other side will be under the root of n1 square minus n2 square is present. So from this now triangle we can write sine theta p opposite by hypotenuse, that is under the root of n1 square minus n2 square whole divided by n1. So similarly we can write our cos theta p also we can write, that is cos theta p. Cos theta p is going to be given as n2 by n1. So theta p is going to be given as cos inverse of n2 by n1 is the value we are having. So theta p is equal to cos inverse of n2 by n1 is present. This is completely what we said to be called as your theta p. So here it is called as sine theta p, that is critical propagation angle formulas. Now put in that one, that is sine theta in formula. So see here, sine theta in is equal to that of n1 into sine theta p. That is equal to n1 into sine theta p. Sine theta p is equal to under the root of n1 square minus n2 square divided by n1. So n1 will get cancelled out. So sine theta n is equal to under the root of n1 square minus n2 square, or theta in is going to be given as sine inverse under the root of n1 square minus n2 square is the value we are having. So this is what we said to be called as the acceptance angle formulas. So theta in is equal to sine inverse of under the root of n1 square minus n2 square. Okay, please copy this, all of you. Said to be called as the fiber core is called as the cladding. N1 core, N2 clad. So this is said to be called as the axis of the fiber. So whenever the light was going to be incident, pass into a fiber, light was going to be incident, pass into a fiber like this. So this angle, so whatever the angle we are having, so this angle was said to be called as theta in and theta in, theta in and theta in, which is called as 2 theta in, is called as cone of acceptance. It's called as cone of acceptance we are having. So next one is said to be called as the solid acceptance angle. If you talk about the solid acceptance angle, is given as a sigma is equal to that of pi into Na whole square steradian. It is measured in terms of steradian we are having. So what is Na? Na stands for the numerical aperture. It's called as the numerical aperture. Theta P is called as the critical propagation angle. It's called as the critical propagation angle we have. So it is completely about our critical propagation angle is present. So now we need to study about this numerical aperture. What is the numerical aperture? Okay. So please copy this part also. Numerical aperture, Na. To talk about the numerical aperture defines about the or describes the light gathering ability of fiber. So numerical aperture is going to be called as the figure of merit of fiber. Next one is numerical aperture is used to measure the magnitude of acceptance angle. So used to measure the magnitude of acceptance angle. So if you see about the numerical aperture, that is Na is going to be given as under the root of n1 square minus n2 square. This is what said to be called as your definition of your numerical aperture we have. So after writing about this one, Na is equal under the root of n1 square minus n2 square. So we studied that sin theta in is equal to under the root of n1 square minus n2 square. Then sin theta in is equal to that of numerical aperture we have. That's called as the numerical aperture is present. So theta in is going to be given as sin inverse of Na. This is the definition. We also give about the numerical aperture. So next one is relative refractive index difference. So relative refractive index difference was denoted by delta. This will tell about that how much difference is present between your core and claddie refractive index. Okay, this is called relative refractive index difference we are having. So delta is going to be given as n1 square minus n2 square divided by 2n1 square we are having. The definition, the relative refractive index difference that is going to be given represented by delta. So n1 square minus n2 square is called refractive index difference. Relatively with respect to the core we are considering said to be called as delta. This is called as relative refractive index difference delta we have. So simplified form. So writing about the simplified form. Delta is equal to n1 square minus n2 square divided by 2n1 square. So it can also written like this also, n1 minus n2 into n1 plus n2, so whole divided by 2n1 square. So we know that n1 is going to be approximately equal to n2. So n1 and n2 are going to be approximately equal. Then we can write delta is going to be equal to n1 minus n2 into value is equal to n1, because we put n2 is also equal to n1. Then they are becoming as approximately equal. So 2 into n1 square. So these two will be get cancelled out. Then delta is going to be equal to n1 minus n2 divided by n1, which is called as your delta. And simplified form, delta can also given like this also, n1 minus n2, see refracting index difference relative with respect to the clad, relative with respect to the core. This is called simplified form we are having. These two parameters are also very much important parameters are considered when you talk about the optical fiber cables. Okay, yes. Copy this part. Next topic is relation between numerical aperture and a delta. Relation between numerical aperture and delta. So that we see about that Na under the root of n1 square minus n2 square. We can write Na whole square. So n1 square minus n2 square is the value we are having. Next, delta. Delta is equal to n1 square minus n2 square divided by 2n1 square. So if we talk about delta, delta is n1 square minus n2 square is replaced with Na whole square divided by 2n1 square is present. Then your numerical aperture Na whole square is equal to 2n1 square into delta. This is the formula we are having. So we can write in this way, your numerical aperture is equal to under the whole root of 2n1 square into delta is the value. So numerical aperture Na is equal to n1 into root of 2 delta is the value we have. This is called as the numerical aperture we are having. And this is said to be called as the another relation. So delta is going to be given as Na whole square upon 2n1 square is present. This is what said to be called as the relation between numerical aperture and delta we are having. Okay, please copy it. It is equation 1. It is called as equation 2. Of course, they are going to obtain from the equation 1 only we got the equation 2. The next topic is light propagation. So talking about the light propagation. Light propagation is of two types. The first one is said to be called as the meridional rays, and the second one is said to be called as the skew rays. So whatever we study up to now is called as the meridional rays. That means in meridional rays, light passes through the axis of fiber and cross the fiber also. That means if you see about the optical fiber cable, having core and cladding, which is going to be shown in the figure, and this is what said to be called as the axis of a fiber. So light rays will going to be cross the axis of the fiber and also pass along the axis of the fiber also. That's what said to be called as the meridional rays we are having. So in the meridional rays, we are also going to having a subclass said to be called as the axial rays. If you see about the axial rays, light passes only through the axis of fiber. Only through the axis of the fiber in the sense means said to be called as core. This one is going to be said to be called as the cladding. And here we said to be called as this one is the axis. And that light ray was going to passing along this axis. So along this axis, the light ray was going to passes, said to be called as the axial rays we are having. So next one is skew rays. If you see about the skew rays, so I can explain here about the skew rays. So if you talk about the skew rays, for your skew rays, the light does not passes through the axis of the fiber. Okay, first point is light does not passes through the axis of the fiber. Does not passes through the axis of the fiber is said to be called as the skew rays we are having. If you consider the skew rays, these are difficult to trace. They are difficult to trace. The skew rays are difficult to trace, and the skew rays are going to be taking a path called as a helical path. They take a path called as a helical path was taken by the skew rays. So if you talk about the next important point about the skew rays, they are difficult to trace, so they are not going to be used in communication systems. If your gamma is going to be equal to 0, then your skew rays will going to become equal to that of meridional rays. So what is this gamma we can see? Most important thing about this skew rays is the acceptance angle of skew rays is very greater than the acceptance angle of the meridional rays. So coupling of light is quite easier. So coupling of light is very easy in skew rays, and very large amount of light was going to be passed into a fiber by using the skew rays. But this is the axis, they are going taking a path like this. Along the axis they can take a path like this. This is called as the helical path we are having. See, they can go and take a helical path like this. The light is going taking a helical path and passing into a fiber. So because of that, they are difficult to trace. So we are not going to be using that skew rays in the optical communication system. So which rays we are going to maximum using is meridional rays as well as axial rays are going to be used. So skew rays are not that much we are using. Okay, so please copy this part. Please copy this part, all of you. This is called as the core and cladding of the fiber, which was as shown in the figure. This is N2 and N1. N1 is the refractive index of core and N2 is the refractive index of cladding. Okay, this acts as a boundary between the two mediums, right? And this is what said to be called as the axis of the fiber we are having. So the skew rays are going to be taking a path said to be called as helical path which is going to be as shown in the figure. It's called as the helical path we are having. Okay, it takes a helical path so that the light was going to be propagated into a fiber. Helical path. So here we can see about that one. So light was going to be come hit here, here. So this is going to be said to be called as 2 gamma. Half the reflection is called as gamma and gamma. So now we can tell about the sine theta in S is equal to under the root of n1 square minus n2 square refractive divided by cos gamma. That value is said to be called as divided by cos gamma is the value we are having. So we can write like this also, theta in S is equal to sine inverse of under the root of n1 square minus n2 square whole divided by cos gamma, and this is called as theta in S. I told in the classroom, if gamma is equal to 0, this point, then cos gamma, that is cos 0, is equal to 1. Then theta in S is equal to theta in, both are same, because sine inverse of root of n1 square minus n2 square is going to be equal to that of theta in is. This is about your skew rays, how the light was going to be propagating. Okay, so please make a note of this one, all of you. So we'll see the numericals and review of optics. So talking about the numericals, the first question, determine the optical power in dBm for the power level of 10 milliwatts. So the input power P was given, that is equivalent of 10 milliwatts is given. Asking to find the optical power in dBm for the power level of 10 milliwatts he was asking. Solution for this one is, so power P in terms of dBm is equal to that of 10 log of base 10 of P. The reference, with reference to 1 milliwatt we are having, so P by 1 10 to the power of minus 3 dBm is the value we are having. That to be called as the optical power. So P is given as 10 milliwatts, so substitute that. So P in terms of dBm is equal to that of 10 into 10 to the power of minus 3 upon 1 into 10 to the power of minus 3. So dBm base 10, this will get cancelled out. So power P was going to be equal to that of 10 dBm is the value we are having. P is equal in terms of 10 dBm is present. Okay, please copy this one. So copy this part, all of you. So next question. Question number 2. Let medium 1 be the glass and medium 2 be the ethyl alcohol. So on medium 2 be the ethyl alcohol. For an angle of incidence of 30 degrees, find the angle of refraction. So find the angle of refraction we are having. So talking about the solution for this one. So medium 1, N1 is going to be given as glass. So for your glass, the refractive index is going to be equal to 1.5. And medium 2, that is considered to be as N2, which is ethyl alcohol. So already we studied in the classroom, ethyl alcohol is equal to 1.36. So to be called as the ethyl alcohol we are having. So angle of incidence is given. So theta 1 is given, that is equal to 30 degrees, angle of incidence. So find the angle of refraction. He was asking to find out what is the angle of refraction we are having. That is theta 2 is going to be equal to how much? Theta 2 is equal to how much he was asking. So according to the Snell's law, so we are using the Snell's law. So whenever we are using the Snell's law, that is given as sin theta 1 upon sin theta 2 is equal to that of value. So value is equal to N2 by N1 is present. So sin 30 degrees and it is equal to sin theta 2. So N2 is going to be equal to 1.36 and N1 is 1.5 we are having. So using your calculators, we are going to be getting that value of theta 2 is equal to 33.46 degrees we are having. So that is what said to be called as the theta 2 value. So here we can going to be just use some conceptual wise also. Your N1 is going to be greater than N2. See, N1 is greater than N2. Then definitely we study in the classroom, that is theta 2 must be greater than theta 1. So theta 1 is 30, so theta 2 will be going to be greater than 30, that is equal to 33.46 degrees we are having. Okay, that's with the conceptual, just knowing about the values what are given. From that you can try to write down the values. Okay, please copy this one, all of you. Please copy that part. Light from free space is incident at an angle theta I to the normal of the facet of a step index fiber the core and cladding refractive index is N1 is equal to 1.5 and N2 is equal to 1.4 respectively. 1.4 respectively. The maximum value of theta I in degrees maximum value of theta I in degrees for which the incident light will be guided in the core of the fiber is dash. So this is the diagram shown having core as well as the cladding. So N1 is equal to 1.5, which is said to be called as the core. N2 is equal to 1.4, which is said to be called as the cladding, and this is said to be called as the normal. So here the light was going to be incident, and this angle was said to be called as theta I. That's the facet normal. The angle is equal to theta I is given. Now asking to find out what is the theta I. Solution for this one. So if you see that whatever the light is going to be incident, and this part is said to be called as the free space. So theta I is called as the your acceptance angle. Okay. So solution for this one is, so sine theta I is equal to under the root of n1 square minus n2 square is the value, and theta I is going to be given as sine inverse of under the root of n1 square minus n2 square. So in the question he was given n1 is equal to 1.5 refractive index of core and n2 is equal to 1.4 refractive index of cladding. So both the two values are given. So theta I value was equal to that of sine inverse of, by substituting these values, under the root of, so 1.5 whole square minus 1.4 whole square is the value we are having. So such theta I is equal to, because you are asking in terms of degrees, that is equal to that of 32.55 degrees we are having. Okay, so 32.58 degrees is the value we are having. Please copy it. So previous gate question. So the next question. So fourth question, the permittivity of water at optical frequencies is 1.75 epsilon naught. We'll stop. It is found that an isotropic light source an isotropic light source at a distance d under water, at a distance d under the water forms an illuminated circular area of radius 5 meters as shown in the figure. So as shown in the figure, the critical angle is theta c. The critical angle is theta c. So theta c is the critical angle. The value of d, in meters is dash. This is a question. So I need to show you the diagram. Okay. So see here. This is the boundary. So it is water which is having 1.75 epsilon naught, and this is air which is epsilon naught. So here we are going to be placing the light source. So the light source was going to be illuminating the light, so which is going to be as shown in the figure. So this distance is going to be equal to that of 5 meters we are having, and this is going to be equal to that of d is the value we are having, that is the d. Okay, and this angle is going to be given as theta c. Theta c is the angle we are having. So whenever the light source was going to be incident less than the theta c was going to be refracted. So light source which was incident with an angle greater than theta c is going to be reflected. The same thing you can going to be find out here also, because it is an isotropic light source which can illuminate equally in all the directions. So we can tell about that less than that will going to be refracted, and greater than that will going to be reflected, which is as shown in the figure. So now he was going to be asking to find out that what is the distance d we are having in meters, he was asking. If you see that here it is going to be forming that theta c we are having, form a triangle. So from that we can find out the value. So solution. So we know that refractive n is equal to n into epsilon we are having. So epsilon is going to be given as that value. If you write here n2 equal to epsilon 2. So theta c is going to be equal to sine inverse of n2 by n1. Can also written like this also, sine inverse of under the root of epsilon 2 by epsilon 1. Epsilon 2 is nothing but the permittivity of the water, and epsilon 1 is the permittivity of the free space or air. Tell about that air or free space. So now we can write about that our theta c is equal to sine inverse of under the root of 1.75 epsilon naught upon epsilon naught is the value. And such theta c value what we are having is nothing but 49.1 degrees we are having. So already I told you such that it forms a triangle. So this was the triangle. This is equal to that of 5 meters. And this is D. See, this forms a triangle which I am going to be showing you here. This forms a triangle. So this is 5 meters and the distance is going to be equal to D, and this value which is equal to that of theta C. So this one is side and D. So can I write like this? Tan theta C. So writing about that tan theta C. If you take that tan theta c, that is going to be equal to opposite by adjacent, which is given by 5 by d. then your distance d is going to be equal to that of 5 divided by tan of theta c, that is equal to 49.1 degrees we are having. So using your calculators you are trying to find out in the distance, that is d. That d is going to be equal to that of 4.33 meters is the distance d we are having. Okay, please copy that part. Right. So another numerical. Okay. So calculate the refractive index of core and clad. Calculate the refractive index of core and clad of a fiber whose numerical aperture is, so whose numerical aperture is 0.22 and the relative refractive index difference is 0.012 is the given question. So it is asking to find out the refractive index of the core and clad, that is N1 and N2 he was asking. And in the question he gave that or the value of Na, numerical aperture is given, Na is equal to 0.22 and delta is also given, so 0.012 is the value of delta. So we know the value of Na and we also know the value of your delta, that is given. Relation between these two is nothing but an asking to find out N1 and N2. What's the value of N1 and N2? So Na is equal to that of N1 into root of 2 delta. So your N1 is going to be given as Na upon root of 2 into delta. So Na is equal to 0.22 divided by root of 2 into delta, 0.012. Then the value of N1. So what is the value of N1? We are getting is equal to that of 1.42 is the value of N1 we have. So value of N1 is equal to 1.42. Next, delta. Delta is equal to N1 square minus N2 square divided by 2N1 square. Such delta is equal to 0.012, 2 into N1. N1 is equal to 1.4 whole square. That is equal to 1.4 whole square minus N2. So by solving this we get our N2 value, that is equal to that of 1.402 is the value of N2 we have. So N1 is equal to 1.42 and N2 is equal to 1.402. These are type of questions that asked mostly in the exams from the topic called as review of optics. If you see that he can ask you about the acceptance angle questions and ask you about the critical angle, and he will also ask you about the what is the numerical aperture present when giving you the two values of N1 and N2, and asking about to find out the values of refractive index of core and clad. Okay, so we can see about the next part, that is types of fibers. So the next topic is types of fibers. So basically if you see about the types of fibers, fibers are going to be of two types, classified based upon the two types. One is called as based on materials, based on the materials. The second type is nothing but it is given as based on the refractive index profile. That is refractive index profile, based upon that profile we are going to be giving you the fibers. So when you see about the fibers that is going to be given based on the materials, first of all, if you study about that based on the materials, so two types of materials are going to be used. The first one is said to be called as the glass, and second one is called as plastic. So each material have its own advantages and disadvantages. So first of all, we see about that the fibers is SCS fibers we are having. SCS fibers in the sense means silica clad silica fibers. It's called a silica clad silica fibers we are having. So the meaning of this one is core and clad both are going to be manufacturing with the help of a glass. That's called as core and clad both are going to manufacture with the glass. If you see about the advantage of this one, so loss is very less. But when you see about the disadvantages, if you see that disadvantages, the first disadvantage is weight is more, and second one is it is, we can tell very clearly such that mechanical strength, or simply we can write strength is less. So the strength wise it is going to be less. So strength is less. Because of core and clad both are going to be having the glass, glass will have brittle in nature. Because of the brittle in nature, what happened is the strength of the fiber is going to be very, very less. So to overcome this problem and also make our loss to be less also, we are going to be using the fibers. Those are said to be called as PCS fibers. If you talk about the PCS fibers, they are nothing but an plastic clad. So plastic clad silica fibers we are having. Class said to be called as plastic clad silica fibers we have. So simple thing is core is manufactured with glass and clad is going to be manufactured with plastic. So beautiful advantage of this one is weight and strength are moderate. So next one is loss is less. So loss is less, so but weight and strength are also moderate, they are going to be less only. But what the major disadvantage of this one is difficulty in manufacturing. Okay, so difficult in manufacturing. So for difficulty in manufacturing we have. So next one is, that is the third one, said to be called as the all plastic fibers. Third one is said to be called as the all plastic fibers we are having. In all plastic fibers, core and clad both are going to be manufacturing with plastic. So manufacturing with plastic. If you see that advantages, the first advantage is strength and weight is we can tell like this, strength is high, first advantage. So second advantage, weight is less. Okay, see, all the disadvantages here will become advantages there, but the disadvantage of this one is loss is high. So what are the loss we are having? So the loss is going to be high we have. So this is completely what we said to be called as your types of fibers that we have, which are depending upon the based on the materials you can see. So please copy this part. Right. So next one is based on a refractive index profile. If you see about the based on the refractive index profile, there are two types of fibers are there. First one is called as step index fibers, and second one is called as graded index fibers. That one is called as the graded index fibers we are having. So step index fiber, the fiber is said to be called step index fiber because the refractive index looks like a step index fiber. If the refractive index is uniform throughout the core and clady, core and clady is going to be having the same uniform refractive index is present, then they are called as step index fibers we have. If we talk about the core, talk about the clady, both are going to be having a uniform refractive index is present throughout the fiber, is called as your step index fibers we have. So when you talk about the step index fibers, so based on the refractive index profile, step index fibers, so consider the fiber of length L having core and clady, which is as shown in the figure. The refractive index of core is N1, the refractive index of clady is N2, and the free space refractive index is N0. And if you are going to be seen about the side view of the fiber, you are going to be find out like this. So this is called as refractive index of core. This is called refractive index of clady is present. But when you see about the profile, if you see the profile of this fiber, so here we can find out that the refractive index is uniform because it's a free space, that is N0. At this boundary condition, the refractive index is changing from N0 to N2, and N2 is greater when compared to N0. Therefore, the refractive index profile was going to be obtained as like this, it is greater. And N2 value is going to be uniform throughout the clad, so N2 is going to remain same. And at this boundary, N2 is now changing to N1. So N1 is going to be greater than N2. So therefore, we can find out such that the refractive index was going to be changes and maintain uniform throughout the core. At the core and at this point, you can find out the change from N1 to N2 once again. So decreases, maintain the uniformity. So decreases because N2 is changing to N0. This is N0, this is N2, this is N1. And the refractive index profile, what we are getting is nothing but an step. If you observe it, this is called as the step, which is called as your RI profile. It is called refractive index profile we have. That looks like a step, so it is called as step index fibers we have. So next, after that RI profile, we can see, we can have the refractive index, so profile we are having. So if you see about that, the refractive index profile of step index fiber is going to be looks like the step. So based on this step index fibers are going to be divided into two types. That's said to be called as refractive index, or we can tell directly step index fibers are of two types based on the diameter of the fiber. Based on the diameter of the fiber. First one is single mode step index fiber, and second one is multi-mode step index fibers. So first one is called as single mode step index fibers. Is called as single mode step index fibers. Second one is called as multi-mode step index fibers we are having. In single mode step index fiber, the diameter of the fiber is going to be very, very less. And in multi-mode step index fiber, we have many modes are present and the diameter of the fiber is going to be very large. So diameter of fiber is going to be large. So first thing that I want to tell to you here is about SMSI. So single mode step index fiber, first point, only one mode is present. Mode means path. So what are the mode we are having? The mode means path we are having, which is called as so mode means path. It takes only one path we are having, and that path is going to be nothing but an axial ray, which is called as the axial ray we are having, that is passes through the axis of the fiber. It's an axial ray. So typically it is going to be having a HE11 hybrid electric mode 11 we are having. So typically HE11 mode we have. To have the single mode is present, the V is called as normalized frequency, which is called as so normalized frequency we are having. So that normalized frequency V number is equal to 2.405 we are going to be taking. So by taking V is equal to 2.405, we are having only single mode is present. So I need to provide you the diagram for that one. Okay, please copy that part. Out of the two fibers, we are going to studying about the single mode step index fiber. Okay, right.